Hey, welcome. Today, we're diving into one of the most fundamental forces in the entire universe. It's a force you deal with literally every single day, and you probably don't even notice it. It's this incredible, unseen power that all starts with a very simple, very familiar experience.
You know exactly what I'm talking about, right? You're shuffling your feet across the carpet, you reach for that metal doorknob, and zap, you get that tiny little shock. Well, that little jolt is right where our story kicks off. It's your own personal encounter with the amazing world of electrostatics.
And that little spark, it's a clue to a much bigger mystery. I mean, think about it. How does a balloon, after you rub it on your head, just magically stick to a wall? Or how do two magnets push each other apart without anything between them? This is the huge puzzle of action at a distance. And you know what? We're going to solve it together right now.
Okay, so to understand these invisible forces, we first have to meet the main characters in this whole drama, electric charges. They are the source of literally everything we're talking about today. The fancy official term for what we're digging into is electrostatics. And it's really just about what happens when electric charges are sitting still, when they're static. Just like the charge that builds up on you right before you get that doorknob zap, it's the science of static electricity. Now, here's what's so cool. This entire complex world is built on just two kinds of charge, positive and negative. And the rules of the game, they're incredibly simple. Opposites attract, so positive and negative charges get pulled towards each other. And on the flip side, like charges repel. They push each other away. That's it. Every single thing we're going to see boils down to that one basic idea. Now, if you zoom way in to a super tiny quantum level, charge comes in these distinct little packets. It's quantized. You can't have like half a charge. But for the world that we live in, for big things like balloons and doorknobs, there are so many of these little packets that we can just pretend it's a smooth, continuous thing. It just makes it way easier to think about. So we know charges either attract or they repel. But how much? How can we actually predict the force between them? For that, we need a rule book. We need to know the law that governs how they interact. And that rule book has a name, Coulomb's law. This is it. This is the fundamental law of electrostatics. It lets us calculate the exact force between two charges, so we know precisely how hard they're going to pull or push on each other. So the force itself, which we call F, depends on two really big things. First, the amount of charge you have on each object. That's your Q1 and Q2. The more charge, the more force. Makes sense. But second, and this is the really critical part, it depends on R, which is just the distance between them. And this is the most important thing to get from Coulomb's law. The force doesn't just get a little weaker as things get farther apart. No, it gets weaker with the square of the distance. So what does that mean? It means if you double the distance between two charges, the force between them drops down to just 1/4 of what it was. It fades away really quickly. All right, so we have a law that describes the force, but we still haven't solved that central mystery, have we? We know what happens, but we still don't know how. How is this force getting from one charge to the other across empty space? I mean, this is the question that really stumped people for a long time. It's not like the charges have little invisible strings they're using to pull on each other. So what is going on in the space between them? The answer is one of the most beautiful and powerful ideas in all of physics, the electric field. See, a charge doesn't directly grab another charge from far away. Instead, it creates this invisible field all around itself that fills up space. And it's that field that then pushes or pulls on any other charge that happens to wander into it. The field is the middleman. And if that sounds a little weird or abstract, well, you're actually already totally comfortable with this idea. Think about gravity. The Earth pulls on you right now, even though you're not touching the center of the Earth. Why? Because the Earth creates a gravitational field around it. The electric field, it works in almost the exact same way, just for charges instead of for mass. And of course, in the real world, charge isn't always some perfect little dot. Sometimes it's spread out all over a surface, or through a whole object, or along a wire. The beauty of the electric field idea is that it works for all of those more complicated real-world situations too. We are almost there. We've got our charges, we've got our forces, and now we have our fields. But there is one last crucial layer to add, and it all has to do with energy. Let's start thinking about this field not just as a place with forces, but as a kind of energy landscape. So let's think about this. If you put a charge into an electric field, that field is going to try to push or pull it. So if you want to move that charge against the force, like trying to shove two positive charges together when they're trying to repel, you have to fight against it. You have to put in some effort. You have to do work. And where does all the energy from that work go? It gets stored. The logic is actually really simple. The field creates a force. Moving against the force takes work. That work gets staved up as potential energy. And that stored energy per unit of charge, well, that's what we call electric potential. Or you probably know it by its more common name, voltage. So that's what voltage really is. It's just a way of measuring the energy difference between two different spots in an electric field. When you see a 9-volt battery, that means there's a potential difference of 9 volts between the two ends. It's ready to do 9 joules of work for every single coulomb of charge that it moves.
Now here's a really neat, almost elegant feature of all this. The electrostatic field is what we call conservative, which is just a fancy way of saying it doesn't care how you move a charge from point A to point B. You can go in a straight line, or you can take some long, loopy, scenic route. The amount of work you do is exactly the same. All that matters is where you start and where you end. Pretty cool, right?
And there you have it. From that tiny little zap from a doorknob to the incredible, awesome power of a lightning bolt, all the way to the battery that's powering the very device you're watching this on right now, it's all governed by these same simple, fundamental rules of charge, field, and potential. The universe is just humming with these invisible forces. And it really makes you wonder, doesn't it? What other unseen forces are out there quietly shaping our world as we speak?